All right, let's dive right into this explainer. We're going to uncover a piece of technology that is quietly saving massive amounts of energy all over the world. You probably don't see them, right? But they're hiding in the basements of skyscrapers, tucked away inside manufacturing plants, and even powering the water treatment facilities in your own city. They're called variable frequency drives, or VFDs for short. And they are, without a doubt, one of the most absolutely crucial tools we have for global energy efficiency. So today, we're going to demystify exactly how they work.
We've got a lot of fascinating technical ground to cover today, so here's our roadmap. 1. The electric motor problem. 2. What is a VFD? 3. The 3 VFD components. 4. Pulse width modulation explained. And 5. The global energy impact. Okay, Section 1, the electric motor problem. To really grasp why this tech is a total game changer, we've first got to look at the massive energy footprint of these hidden workhorses. Take a second and just guess. How much of the world's electrical energy is consumed by electric motors alone? Just keeping industrial motors, pumps, and fans spinning. What do you think? 10%? Maybe 20%? Well, the staggering reality is it's more than half. Over 50% of all global electrical energy goes straight into electric motors. Think about that for a second. That makes motor efficiency an incredibly high-stakes issue for our power grids and, our climate as a whole. And here's the core of the issue. The old one of running things like city water pumps or massive industrial fans is honestly just terribly wasteful. Traditionally, an electric motor just runs at a fixed, full speed, 100% capacity all the time. So if you need less water flow, you don't slow the motor down. Instead, you use mechanical brakes, or you partially close a physical valve to just choke the flow. It's literally the equivalent of driving your car with your foot mashed on the gas pedal and using the brake pedal to control your speed. Crazy, right? It causes massive mechanical wear and just tears through energy. But the new way? It's all about adjusting the motor speed directly to match exactly what you need. So, finding a solution to all that waste brings us to Section 2. What is a VFD? Basically, it's the motor's brain. A variable frequency drive, which you might also hear called an AC drive, a micro drive, or an inverter, acts as this smart controller. It sits right between the electrical power supply and the motor itself. What it does is constantly adjust the frequency and the voltage being fed into the motor. This lets the motor smoothly ramp up or scale back its rotational speed, perfectly matching whatever load is required at that exact second. Now, to really get how the VFD pulls off this magic trip, we gotta quickly differentiate between two types of electricity. On one side, we have alternating current, or AC. That's the power the grid supplies to your house. The electrons in AC power are constantly reversing direction, flowing forwards and backwards, kind of like ocean tides moving in and out. On the flip side, we have direct current, or DC, like what comes from a battery. In DC, electrons flow smoothly in a single direction, like a river flowing downstream. Here's the catch. An AC electric motor needs that alternating current to spin, but trying to directly control the speed of that AC power is notoriously difficult. Which leads us perfectly to Section 3, the 3 VFD components. It's super interesting to trace the exact journey an electron takes through these 3 stages to solve this exact problem. To control that motor perfectly, the power actually undergoes 3 main conversions. Step 1, the rectifier, converting AC to DC. Step 2, the DC bus for smoothing. And Step 3, the inverter, turning that DC back to AC. Let's start with Step 1, the rectifier. The unpredictable AC tide from the grid enters here, and it usually hits 6 diodes. You can think of diodes using a really simple plumbing analogy. They act exactly like check valves in a water pipe. They only allow electricity to flow in one single direction, completely blocking it from reversing back. So by forcing that alternating tide through these one-way valves, the VFD turns the alternating current into a direct current. But at this stage, it's not a smooth flow yet. It's actually a really rough, pulsating direct current. And that brings us to Step 2, the DC bus. This acts as the system's filter, using components called capacitors and resistors. Going back to our plumbing analogy, if the rectifier's output is like water violently surging through a pipe, the capacitor acts like a giant water reservoir or an accumulator tank. It absorbs those excess surges and fills in the gaps when the pressure drops. So it effectively smooths out all those rough voltage ripples into a nice, clean, flat, constant flow of direct current. Finally, we hit the 3rd stage, the inverter. This is where the real magic happens.
The inverter takes that perfectly smooth DC power and converts it back into AC power. It does this using a set of fast-switching transistors, specifically ones called IGBTs. Imagine these transistors as super-fast plumbing valves. By rapidly turning these valves on and off in perfectly timed pairs, the controller dictates exactly which path the electricity takes. It essentially turns that one-way river back into a carefully controlled alternating tide.
All right, Section 4, Pulse Width Modulation Explained. How exactly does flipping a switch on and off create a smooth wave?
Because think about it, a switch only has two states, right? It's either completely open or completely closed, 100% on or 100% off. So how in the world do we make a rolling, variable, alternating current from a flat, direct current using just simple on and off switches?
Well, the secret to this whole engineering marvel is a brilliant process called pulse width modulation, or PWM for short.
This is where modern microprocessors really show off. The VFD's controller rapidly pulses those transistor switches open and closed thousands of times per second. I mean, sometimes up to 16,000 times a second. But here's the genius part. It constantly adjusts the width, or the duration, of each pulse. If it leaves the switch closed for slightly longer periods, it builds up a higher average current. Leave it open longer, the average current drops. When you string thousands of these varying pulses together, the motor itself effectively smooths them out. The motor experiences an average current that perfectly simulates a beautiful rolling AC sine wave. And because the VFDs can change the width of these pulses instantly, it has total control over both the voltage and the frequency. That means it dictates the exact precise speed of the motor. Which brings us to Section 5, the global energy impact. Understanding the nuts and bolts is cool, but the real-world savings are what truly matter here. Because the VFD uses pulse width modulation to dial back the power electronically, instead of mechanically choking the system with physical valves or brakes, the efficiency gains are just incredible. For things like centrifugal fans and pumps, the physics of fluid dynamics dictates that reducing the motor speed by just 20% can actually chop energy consumption in half. Installations on fans and pumps routinely see average energy savings of 40%, and in some specific variable torque applications, you can hit up to 80% energy savings. You're giving the motor exactly what it needs and literally not a single drop more. To really put the scale of this into perspective, listen to this quote from the OMDIA COP26 Global Report. If all fans and pumps were equipped with VFDs, the savings would equal the entire power generation capacity of the EU. Let that sink in for a second. The entire EU. We aren't talking about building massive new solar farms or wind turbines here. We're just talking about making the motors we already have run a whole lot smarter. Upgrading existing motors with this one piece of tech is an absolute cornerstone for global decarbonization. So we know that more than half of the world's electricity gets eaten up by motors. We know that running them at full speed and choking them with valves is completely backwards. And we know that an elegant, proven solution exists right now with the variable frequency drive. So the ultimate question I'll leave you with today is this. Knowing all of this, how quickly can we actually implement VFDs across our global industries to reach our critical climate targets? The technology is ready and waiting. Now, it's just a matter of making it happen.